So how do we take all this stuff with transformations and have them work with double integrals? How do we actually work with this chapter with this new concept? Well, let's say we have a transformation t. Remember that it's taking in the variables uv and giving out the old variables x, y. And we want to see what does t change about the area of a small rectangle. If we're working over here in the uv plane and we have some small rectangle, make this. I'm going to draw somewhat big just so we can actually work with it, but this is supposed to be rather small, and we're going to get estimates for how the area changes that will get better as it gets smaller. So all this is going to be approximation until we get to a result at the end. So S here changes into some region. That we call R. So here, this point here corresponds to this point here. This point here actually corresponds to this point here. This point here corresponds to this point here, and so on and so forth. I'm going to go ahead and name this point that we have here. I'm going to call this U0, V0. This side over here is going to have a length of delta U. This side over here is going to have a length of delta V. So you can actually say this point here is U naught plus delta U, comma V naught. This point here is U naught, comma V naught plus delta V. So let's even go ahead and put those in here. We'll be using those points as we go. Of course, over here, this is the point T of U naught V naught, and then T of U naught plus delta U V naught, whatever the results of plugging those points into T. And we want to say we know that the area of S is delta U times delta V. I mean, it's just a rectangle. What is the area of R, or at least what approximately is the area of R in terms of the stuff with S? Now, one thing that we're going to do is we're going to introduce vectors. We're going to look at t in terms of vectors. We're actually going to define a new function. This is going to be r. The book has this as a bold r. You could put this as r with an arrow over it if you want to. I'm just going to write r. R of uv is going to be the vector where I'm going to use the x value from our transformation times I. So I here being the unit vector along the x-axis. Then we'll have y of uv, so the y coordinate of this transformation, times j. So really all I'm doing here is the first component. The x component is the x value of t. The y component is the y coordinate of t. So r is really just t, just with its outputs interpreted as vectors instead of as points. So not really a brand new thing, but a different way of viewing it. Now we want to use this by looking at various curves. So this boundary curve here, this line, this horizontal line, and I don't know why I decided to delete that. This horizontal line turns into this curve here. And we can actually view that as a parameterized curve. It is the curve with parametric equations. X is equal to x of u comma v naught. So because v naught is constant here, so we keep v naught constant, but we let u change from u naught to u naught plus delta u. And we have y equals y times u v naught. So these are parametric equations for a curve. and we can actually get the tangent vector to that curve, basically the vector that is tangent to that curve at this point, by differentiating. Basically, the derivative of this function with respect to u, because v naught's a constant, and then the derivative of this vector, of this function with respect to u, because v naught, again, is constant. Now, since we aren't treating this as x and y as functions of two variables, those derivatives with respect to just u are the partial derivatives of these two with respect to u. In other words, we have a vector that is the tangent vector to that curve, which we're going to denote as r sub u, is the partial derivative of x with respect to u times I, plus the partial derivative of y with respect to u times j. So this is a tangent to our curve. And we write that as r sub u because we're really kind of taking the derivative of this up here. So that we're kind of taking the partial derivative of r would be taking the partial derivative of the first component and then the partial derivative of the second component. That's the way we want to view it. And in fact, we're going to be doing stuff like that in the next chapter as well. Now, we're also going to work with another vector. Let's look at the vector that comes from this base point to this point over here. So we have some vector that points from here to here. That means we just plug in u naught v naught and u naught plus delta u v naught into t. Well, that gives us the 2 points, but we could also plug them into r. That considers those 2 points as actual vectors, and then the vector between those two endpoints is actually the difference between those two vectors. So this vector here is actually the vector r of u naught plus delta u v naught minus r of u naught v naught. If we take that vector there and we divide it by delta u, this format should look somewhat familiar. In fact, as we take the limit as delta u goes to 0, this is a derivative. In fact, it is the derivative ru. It is literally just this vector here. And so what we can kind of say is that this vector, this ru, well, at least times delta u, is approximately equal to this difference, as long as delta u is smaller. And that's going to be kind of the key. So getting this approximation is kind of key. Because what we can kind of do is do the exact same thing, but instead look at our v direction. So if we have a tangent vector coming off like that, we could say that's r sub v. But then we also have this vector pointing from here over to there. That's the difference between, in this case, r of u naught v naught plus delta v minus r of u naught v naught. And then we kind of think, well, if we take that vector and that vector there and kind of complete a parallelogram, might be a little hard to see here. Maybe if this kind of is a little bit confusing, maybe take a look at some of the pictures in the book. But the idea is we have two vectors here that we complete a parallelogram for, and we want to estimate the area of R as approximately the area of that parallelogram. But because that parallelogram involves these different points, we're going to approximate that area of the parallelogram using the derivatives of the function and only looking at the tangent vectors at the point u naught v naught, or t of u naught v naught. Well, the area of a well, okay, let me input that. So the area of R is approximately the area of the parallelogram should say using the differences, which is then approximately equal to the area of the parallelogram using the derivatives. But the area of the parallelogram using derivatives, remember there we're dealing with the vectors delta u times ru and the vector delta v times rv. So we have these lengths along the rectangle, and then we have the vectors of our tangent vectors, or the tangent vectors to the various boundary curves. Now, if we have two vectors that we want to find the area of the parallelogram determined by that, remember back in chapter 12 we had a formula for that. In fact, it is literally just take the not the absolute value, the magnitude of the cross product. So we're taking this vector here crossed with this vector here. Of course, the delta u and the delta v, those are constants. Well, they're not really constants necessarily. We're actually going to let them go to 0 eventually, but they're not part of the vectors. They're scalars. That's what I should say. So really, we can go ahead and pull those out. We get the cross product of ru and rv times delta u delta v. Or really, the delta u delta v is the area of the original rectangle, where essentially the area of our new region, the area of this R, is some multiple of the area of this S. And that multiple depends on our tangent vectors. And those tangent vectors, of course, come from the partial derivatives of x and y with respect to u and v. Let's actually simplify that, though. This is not really the expression that we want. What is this cross product? Now, one thing I should note here is that we are taking the cross product of two vectors of two variables. We're working in 2 dimensions right here. Since the cross product only really works for 3 dimensions, we're assuming here that we have a plus 0k at the end of all these. So when we actually take the cross product, we have partial of x with respect to u, I, plus partial of y with respect to u, j, plus 0k. That's the idea that we have. And then we can do the same thing with the RV. But one thing I'm going to do here, because it is actually kind of important for the formula that we're going to get at the end, is I'm going to use determinants. I've kind of been avoiding determinants because I'm not entirely sure if every one of you does know how to use determinants, but it actually is kind of important here. So in determinants, we take a 3x3 matrix where the top row here is ijk, second row here is going to be ru. Ru was partial of x with respect to u, partial of y with respect to u, and then 0. Rv is a third row. That is partial of x with respect to v, partial of y with respect to v, and then 0. And then we want to simplify this determinant. Now, if you don't remember how this works, or you haven't seen how this works, just kind of roll with it. It's mainly to get to a formula, and then we'll use that formula in the applications from this point on. We won't have to come back to here. But in order to actually take this determinant, we take this I times everything that excluding this first row and first column, so the determinant of this 2x2 over here, But since we do have two zeros there, that determinant actually turns out to always be 0. Then we do the same thing with j. We take out this row and this column and look at the determinant of the 2 by 2 that's left. But because we have two zeros, that one always turns out to be 0 as well. So far so good. We have two zeros, but then when we get to k, now we take out the first row and third column, we're left with this 2 by 2. That one may or may not be 0. And in fact, we hope it does not turn out to be 0, because that will actually make our formulas not work very nicely. We don't want to have 0 overall. We want something to not be 0. But we get this determinant times k. And the reason why we don't want this to be 0 is that this is actually the magnitude. This determinant, since k is just a unit vector, the determinant, the magnitude of this vector is actually, well, the absolute value of this determinant is actually going to be this multiple, this magnitude of RU cross RV times the area of the original S. And we don't want the area of R to be 0, because then we're dealing with something that is no longer some two-dimensional region. We don't want to be dealing with negative areas here either. We want the area of R to turn out to be some positive multiple of the area of S. And that multiple is going to be essentially this determinant. Technically the absolute value of the determinant. So we're going to give this determinant a name. We call this determinant the Jacobian of the transformation, named after mathematician Jacobi. Technically here they've swapped the partial of u with respect to, partial of y with respect to u with the partial of x with respect to v. They have them in the opposite order here. In terms of the determinant, that doesn't matter. It actually gives you the same result overall, because the way you find that determinant is by multiplying the first diagonal here, then subtracting the product of the other diagonal. And if you're just swapping two things that are being multiplied together, I mean, it doesn't change the result. Note here that the Jacobian is not the absolute value of this determinant. It is actually just the determinant itself. Our formula is going to require us to take the absolute value of that as we go. And we use the notation of d of both the two both the two old variables divided by both the d with both the two new variables. And then when we do that, we can actually set up a Riemann sum. Basically, we have that the double integral over R of some function f of x, y, dA. This is approximately some Riemann sum. Obviously, we're approximating things here. This is not super precise or anything like that. But the idea here is that we take sample points for x and y that we plug into f. We have some delta a's. We can even say delta aij's. We approximate this thing using our transformation. So we're still summing over i's and j's, where we have f of our new function, our new variables. So instead of x here, we put x at the sample point where we have u and v, and then y with our sample point for u and v. So that's just a matter of plugging in our formulas for x and y in terms of u and v into our function. But then the delta a, our area of our little subsections, these are the areas of r's. The r's, remember, these are going to be our Jacobian, or the absolute value of our Jacobian, times delta u. Yes, you could say delta ui and delta vj. Because we're just looking at this area as this thing, where we've used the Jacobian in here because that's what we we found it to be. And then once we've done that, well, we can say that we can essentially turn this into a double integral. As we take our limit, we end up with here f of x of uv, y of uv. This Jacobian actually stays as it is. And then these turn into a du and a dv. Of course, we'll have to eventually determine our limits for ourselves. And I've written this as an approximation, but it can be proven that under certain conditions, this is actually an equality. So this kind of starts off with a big block of text, saying stuff like that T has to be a C1 transformation, its Jacobian has to be non-zero, because we don't want our areas to suddenly change from positive areas to zeros. Our T maps some region S in the UV plane to some region R in the XY plane. Our function we want it to be continuous, and we want our regions to be at least somewhat well behaved. They write here that R and S are type 1 or type 2. That's actually a little bit more than we need, but we do want them to be relatively well behaved. And we also want that T itself to be, well, the one-to-oneness is kind of already taken care of by the fact that the Jacobian is non-zero, though we should probably state it anyways. But we do allow it to be not one-to-one on the boundary. That's useful whenever we deal with anything with polar coordinates, especially. But it'll be useful in other situations as well. But in all those conditions are satisfied, which is usually going to be the case. It sounds like a lot, but it really isn't. Under those conditions, we have our formula. We have what we call the change of variables formula for double integrals. Let's actually look at how this works with polar coordinates, because that's the one that we're most familiar with. So remember there, we know that x is r cosine of theta, y is r sine of theta. We want to compute the Jacobian of this transformation. So remember that d of xy, d of r theta. This is going to be a 2x2 determinant. That 2x2 determinant is going to have all of our derivatives in it. So what are the derivatives? What is the partial of x with respect to r? Well, cosine of theta here is a constant. R is going to go away, so we get cosine of theta. We can do pretty much the same thing. The partial of y with respect to r is going to be sine of theta. The partial of x and y with respect to theta is a little bit more complicated because you actually have to differentiate the trig function, but the r is just kind of there as a constant to stick around. The derivative of cosine is negative sine. So we have a negative sine, but then we have the r still there. Derivative of sine is a positive cosine, and the r is still there. We take these things, we put them into our 2x2. Now, if you don't remember whether or not you put the r's on the first row and theta's on the second row, or you put the x's on the first row and the y's on the second row, it really doesn't matter. Essentially, if you flip this over the main diagonal, it's not going to change the result. So I'm just going to take the values that we have here in the order that I put them into our 2x2. So we have cosine of theta here, we have sine of theta here, then we put the negative r sine theta here, and the r cosine theta here. Again, if you do it the wrong direction, you'd be putting the negative r sine over here and the sine up here, but you're going to get the same result, so it doesn't matter. When you take the determinant, again, you multiply along the diagonals and subtract the one here. So you're going to get cosine of theta times r cosine of theta, or in other words, we have r cosine squared. Then we're subtracting a negative, so we're adding r sine theta times sine theta, so even r sine squared theta. Of course, we can go ahead and factor out an r. We have cosine squared plus sine squared, which is just 1. So actually that turns into r times 1. It turns into an r. The Jacobian of polar coordinates is r. If we write that into our change of variables formula, so our integral over some region in the xy plane of some function of x and y. So let's just write this, instead of putting dA here, let's put dx dy, just to specify that we are working in x and y variables instead of r and theta. So the integral over some r is the integral over some s. You have to figure out exactly what the s and r, what those actually are in whatever case you're actually working with. I just want to write down the formula here. X is going to be replaced by r cosine theta. Y is going to be replaced by r sine theta. We put in the absolute value of our Jacobian. So we're putting this thing in there. Here we are going to be assuming that r is a positive value, or at least a non-negative value, so we don't actually have to put in absolute value signs. Pretty much any time we are actually doing any applications using polar coordinates, we kind of assume that, though we didn't really state that explicitly. But this works specifically because we're making sure that r is positive. And then of course we put in du dv is actually in this case dr d theta. And that's exactly the formula that we got before. This extra r, the extra r that we kept always seeing, is actually just the Jacobian of polar coordinates. That's all what it means. It's this particular value that comes from our transformation rule. And we're going to see kind of the same thing with, well, we're not going to go through for cylindrical coordinates, but we are going to derive it for spherical coordinates, because that's the one that's actually a little bit more complicated and a little bit more new to us. But we'll see that when we do triple integrals. In fact, let's actually get into triple integrals right now, before we even start doing some examples. So for triple integrals, we're not going to try to derive the formula. Like you can see, we spent a lot of time deriving the formula for double integrals. I'm just going to give you the formula, and we'll talk about exactly, we'll go through spherical coordinates and all that kind of stuff. But it's just not worth trying to get through all that stuff. The book doesn't even go through it as well. So it just gets even more complicated when you're trying to do all that stuff. But what we're going to have here is we're going to have some transformation that takes in variables u, v, and w, and gives you variables x, y, and z. X, y, and z are functions of u, v, and w. And we can define the Jacobian of this transformation, again, as a determinant of all the partial derivatives, of all the first partial derivatives of x, y, and z with respect to u, v, and w. Of course, there are 9 of them. So we have this 3x3 determinant, and you really cannot avoid using determinants here. If you were to try to write this out, like they actually did when it came to 2 variables, with 2 variables they actually just wrote it out, and you could use that formula if you want to. With 3 variables, this is actually a very long, really long expression. It's technically 6 different terms. Each of the terms involves the product of 3 different things, and trying to remember the actual format of that directly without referring to the 3x3 determinant is actually way overcomplicated. No one actually does that. So that is why we're specifying that we actually need determinants in this section. Now, if you don't know how this all works, if you don't know how determinants work, don't worry too much. I'm not going to ask you to do anything with triple integrals other than with the cylindrical and spherical that we've already done before. In fact, I don't even know if I think the book only has like one problem that even involves triple integrals in this section. It's important that you know that it can be done, and if you're going to use it anywhere in the future, maybe you can actually remember that we have it here, and by that point you know how to work with linear algebra and determinants, at least the basics of how those work. But since this class does not have linear algebra as a prerequisite, I can't assume that you know how to do that yet. But assuming you know what the determinant is, you have this Jacobian, and we can actually write down a formula for change of variables. So the triple integral over some region R in the XYZ space. So we have some, maybe a blob in X, Y, and Z. We have our R here. We have some S over here. Hopefully it's a little nicer. Let's just go ahead and draw it as a box, maybe. In our UVW. Technically, our transformation is going this direction. So we're wanting to integrate over this blob R in XYZ space. Instead, we get to integrate over S in UVW. We end up just plugging in our formulas for X, Y, and Z in terms of UV and W into the X, Y, and Z. We multiplied it by the absolute value of our Jacobian, whatever the value of this thing is, and we just use du, dv, dw. So it's essentially the same formula. In fact, both the change of variables formulas for 2 and 3 variables were essentially the same kind of formula that we had for a function of one variable. If you go back to the other video and where we talked about our formula for substitution, it was essentially we introduced a derivative. The Jacobian here is just playing the role of our derivative. It's just we have to be a little bit more careful about the signs when we get to higher dimensions, just because things don't generally are a little trickier to work with. But the point here is that we really just get to plug in our formulas for our variables. We introduce a derivative in a sense that's an additional multiplier, and then we get to work in our new variables. Let's see how this works in spherical coordinates. So remember, in spherical coordinates, x is equal to rho sine phi cosine theta. Y is equal to rho sine phi sine theta. Z is equal to rho cosine phi. We're going to need the derivatives of x, y, and z with respect to all three of these variables. We have 9 different derivatives here. So this is going to take some space. So let's start with rho. Derivative of x with respect to rho. Well, sine phi and cosine theta don't depend on rho, so that's a constant. The rho just ends up going away. If we differentiate x with respect to theta, now the rho sine phi don't matter. There's just a constant that come along for the ride. The derivative of cosine theta is a negative sine. So we'll still have the rho sine phi, but then we have a negative sine theta. And then the derivative of x with respect to phi, this time the rho cosine just stick around. Derivative of sine phi is cosine of phi. So we have rho cosine phi cosine theta. We do the same thing for y. And hopefully by this point, I don't really need to explain every little step. The rho goes away. For theta, now the sine of theta turns into a cosine of theta. Everything else stays the same. And then for phi, this time the sine of phi changes to cosine of phi. Z is actually a little nicer because it doesn't even have any thetas. Derivative with respect to rho is just going to be that cosine of phi. Derivative with respect to theta, since there are no thetas, that is actually just 0. So actually really nice there. And with respect to phi, now the cosine turns into a negative sign, so we have a negative rho sine phi. If we take all this stuff and put it into a matrix, then we get our Jacobian. So we have d of xyz, d of rho theta phi is a 3×3 determinant, which I'm just going to go ahead and write them in here. These are going to be the same ones that we had on the previous page. So kind of a big determinant here. It's a 3×3 determinant. If you don't know how to work with 3×3 determinants, just kind of roll with it, and you'll just have to trust me that we can evaluate them this way. Even if you have seen 3×3 determinants, maybe you don't know the easiest way to tackle this. So you might only know the way to expand along the first row. The kind of the way we did it with actually evaluating our area of the parallelogram earlier, where we had ijk on the top row. That's probably the easiest way to default to it. But this one actually, because of the 0 here, is easier to expand along the last row. So what you do there is you take the cosine phi, take out that row and column, and look at that 2×2 determinant. You end up with a cosine phi times the 2×2 determinant from up here. So we have a negative rho sine phi sine theta. We have a rho cosine phi cosine theta. We have a rho sine phi cosine theta, and a rho cosine phi sine theta. Then we subtract 0 times what happens if you take out this row and this column. Of course, because of the 0 there, that goes away. That's why we want to expand along that. That's why it becomes a little easier. And then we move on to this one, where add, or really subtract because this is negative, negative rho sine phi times the determinant of take out this row and this column, so you're left with this 2×2 over here. So you have a sine phi cosine theta. Here we have a sine phi sine theta. We have a negative rho sine phi sine theta, and a rho sine phi cosine theta. Now each of these is a 2×2 determinant. We have to evaluate them. Remember, that's just what we just take the diagonals, multiply them together, and subtract. So we end up with when we multiply this and that, we have 2 rows. We have that minus sign. We have a sine phi. Sorry, that should be squared. Sine phi. We have a cosine phi. And then we have 2 copies of sine of theta. Now we subtract this one, so it's minus. We have 2 rows. We have a sine phi and a cosine phi. And then we have 2 copies of cosine of theta. Then down here we have minus rho sine phi. We again have to do the diagonals, so we have a row. We have 2 copies of sine of phi. And we have 2 copies of cosine of theta. We subtract, or really add because there's a negative there, plus we have 1 row. We have 2 copies of sine of phi. We have 2 copies of sine of theta. And now we want to see what can simplify. Now the first thing to note here is inside this parentheses, we have a negative rho squared sine phi cosine phi in both of these 2 terms. If we factor that out, if we pull all that out, we end up with a sine squared plus a cosine squared. That turns out to be a 1. But we have to remember we're taking this cosine phi times all that stuff. So we'll end up with a negative rho squared. We still have one copy of sine of phi, and we had one copy of cosine phi, but we have another copy now. So we have a sine phi and two cosine phis. Here, this again, we can actually pull stuff out. We can pull out a rho sine squared. Then we're left with cosine squared plus sine squared. Again, that's a 1. Keep in mind those are both a theta. If one of them was phi and one of them was theta, we couldn't do that. They're both a theta, so keep that in mind. So we have that rho sine squared. We already have a minus rho and another sine outside. So we'll have minus 2 rhos. Technically, we have 3 sines of phi. I could write that as sine cubed if I wanted to. I'm going to write that as sine times sine squared of phi. And the reason why I want to do it that way is because now I can recognize here that both these two terms that are left have a negative rho squared sine phi in them. I can pull that out, and I'm left with a cosine squared plus a sine squared. And so that becomes a 1. Ultimately, everything comes down to a negative rho squared sine phi. And that's important, because when we actually put that into our formula for change of variables, we have the integral over some region in terms of x, y, and z of a function of x, y, and z is equal to some region in rho theta phi, f of our formulas in terms of rho theta phi. Just going to have to write all those out. And I'm going to have to write down below now. It's taking up a lot of room. So those are just the formulas for spherical coordinates put in for x, y, and z. Then we put in our Jacobian, or really the absolute value here. So the absolute value gets rid of that negative because rho is going to... We're keeping rho... Well, actually, rho squared is positive, so yeah. Don't even have to worry about the rho, actually. It's more because with phi, we're only looking at values of phi between 0 and pi, and that means that sine of number of angles between 0 and pi are positive. So rho squared sine phi is positive, so we have to get rid of the minus sign. So this times rho squared sine phi, that's the absolute value of our Jacobian. Then we have d rho, d theta, d phi. But the important thing here is that this is the formula we had before. Our Jacobian, whether it had the minus sign or not, gives us the rho squared sine phi that we already derived that we need to have in their first spherical coordinates. The fact that the Jacobian we calculated for spherical coordinates, the fact that we did get a minus sign here, some people actually take issue with that. That is one of the reasons why there are different notations and different orderings for these variables for spherical coordinates. One solution people like to do is swap the phi and the theta and the phi. If you do that, it swaps everything here, and switching 2 columns or 2 rows actually does change the sign of a determinant. Ultimately, that's not really going to matter for us because we just took the absolute value. But just be aware that's one of the reasons why people like to do things slightly differently for this. But obviously the point here is the rho squared sine phi, that extra term, that extra factor in there, was just our Jacobian. It's just we're doing a change of variables, we get an extra derivative factor, essentially. And that's the particular factor that we can calculate fairly easily, with not having to go through all the geometry that we did originally for our spherical coordinates. As long as we have have equations, as long as we can write out x, y, and z in terms of those variables, we can easily calculate, as long as we know how to take determinants, what that Jacobian should be, without having to get into the geometry of stuff. And that's really nice. All right, but I'm going to put some examples. I'm going to actually work out some double integrals. We're not going to do any triple integrals. Not going to ask you to do any of those, but I do want to definitely go through some examples in the next video for double integrals. So I'll see you in that one.